A-level mechanics, kinematics, energy. Let's have a look at what we mean by energy in mechanics. Now, if a body is able to do some work, then it's said to have energy, and the amount of energy it has is the amount of work it's capable of doing. Now, energy comes in many forms. If we consider a car, it stores its energy in the form of petrol. Once the petrol runs out, the car stops working. A toy might store its energy in the form of a battery. Again, once the battery runs out, it'll stop working. However, in mechanics, we're going to look at only 2 or 3 simple forms of energy. For example, in the diagram, if the surface is frictionless, when block A is released, it will move down, thus pulling block B and doing some work on it. If a body has energy and does some work, then it loses some of its energy. If work is done to a body, then it gains energy. Work can be converted into energy, and energy can be converted into work. They're both measured in the same units, joules. Now, as I said, there are many types of energy: heat, chemical, nuclear, sound, light, and many more. In mechanics, we consider 2 types, kinetic energy and potential energy. Here we look at gravitational potential energy, but later we may also look at elastic potential energy. Let's start by looking at kinetic energy. Now, the kinetic energy stored in a body is the energy it has due to its motion. If a moving body collides with another body, it can cause it to move, thus doing work on the other body. To see how much energy there is in a moving body, consider a body of mass m resting on a smooth horizontal surface with a constant horizontal force F acting on it. Now we have F equals ma, and so A is equal to F divided by m. Suppose it starts from rest and after travelling a distance d has velocity v. Then, using the equation v squared equals u squared plus 2as, we have, to start with, u is 0, so v squared equals 0 squared plus 2ad. But a is equal to f over m, so we could write v squared equals 2 times f over m times d. In other words, mv squared is 2 times f times d, or a half mv squared is equal to fd. But fd is the force times the distance moved, so it's the work done on the body. So the work done on the body is a half mv squared, which means the body now has kinetic energy, a half mv squared. Now that's an important formula. The kinetic energy is equal to a half mv squared. Now let's look at potential energy. The potential energy of a body is the energy stored in a body due to its position. Now we'll be looking particularly at gravitational potential energy. We have seen that if an object can move down, it's capable of doing work. Consider a body of mass m being raised at a constant rate by a light string. We can mark in the forces. The weight is mg and the tension is T. And if it's being raised at a constant rate, then T is equal to mg. If the body is raised an amount h, then the work done is T times h. Now T is equal to mg, and so the work done is mgh. So, if a body of mass m has a height h, we say it has potential energy mgh. But note, it is important to define where the height is measured from. This is usually ground level, but it can be taken anywhere. This does mean that if the body is below 0 height, it has negative potential energy. So, potential energy can be negative, although kinetic energy is always positive. Let's look at an example. Consider a body of mass m resting on a smooth plane which is at an angle of theta to the horizontal. We can mark in the forces acting on it. There's gravity acting vertically down, and that's mg, and there's the normal reaction r, which is perpendicular to the plane. Now, suppose it's released from rest and slides down the slope a distance d. Resolving down the slope and using F equals ma, we have the component of mg down the slope is mg times the cosine of the angle between the vertical and the slope. So, mg cosine of 90 minus theta equals ma, and we can divide both sides by m, and remember cosine of 90 minus theta is sine of theta, so g sine theta equals a. Now if we use the equation v squared equals u squared plus 2as, we've got, it starts from rest, so u is naught. We have a equals g sine theta, and the distance s is d. So that gives us v squared equals 0 squared plus 2g sine theta times d. But if we look at the triangle underneath the slope, we see that h is equal to d sine theta. So that gives us v squared is equal to 2gh. And if we multiply both sides by a half m, we get a half mv squared equals mgh. So we see the kinetic energy gained is equal to the potential energy lost. Now we can use this principle that the total amount of energy remains constant to find some easy solutions to quite a number of problems. Let's have a look at another example. The diagram shows a 6 kilogram mass resting on a smooth plane at 30 degrees to the horizontal. It is attached by a light string over a smooth pulley to a mass of 4 kg suspended from the string. The masses are released from rest. Find the velocity of the masses after travelling a distance of 2.4 meters. Well, to solve this, we can do it by considering energy. The 4 kilogram mass descends 2.4 meters. The 6 kilogram mass will then go up the slope 2.4 meters, but vertically it ascends 2.4 times sine theta, which is 1.2 meters. So the total energy lost is the energy that the 4 kilogram mass loses minus the energy that the 6 kilogram mass gains. So the potential energy lost is 4 times g times 2.4 minus 6 times g times 1.2, which works out to be 2.4 g. Now both masses start from rest and accelerate up to a velocity v. So the kinetic energy gained is a half times 6v squared plus a half times 4v squared, which is equal to 5v squared. So we have 5v squared equals 2.4g, and if we divide by 5, v squared is equal to 2.4 times 9.8 divided by 5. In other words, v squared is equal to 4.704. Now if we take the square root, we get v is the square root of 4.704, which is 2.1688. So we have as our answer, the velocity is 2.17 meters per second. We have an important principle here called the conservation of energy. If we have a body on which the only external force doing any work on it is gravity, then the total kinetic and potential energy will remain constant. Let's look at another example, example 3. A pendulum consists of a small weight on the end of a light string. It's held to one side at 45 degrees and released. What velocity will the weight have when the string is vertical? Well, to solve this we can use the conservation of energy. take the lowest point as 0 height. That means the pendulum has initial height h and velocity 0, and the pendulum has a final height of 0 and velocity v. So initially mgh plus 0 equals finally 0 plus a half mv squared. If we double both sides and divide by m, that gives us v squared equals 2gh. Now if we look at the diagram, we can draw a horizontal line across to create a triangle. And from the triangle, we can see the adjacent side of the triangle is 2.8 times the cosine of 45 degrees. So we have h in our equation is 2.8 minus 2.8 cosine 45. So this gives us v squared is equal to 2 times 9.8 times 2.8 minus 2.8 cos 45, which works out to be 16.0735. So v is the square root of that, which is 4.00923. So we have the velocity at the lowest point is 4.01 meters per second. In example 4, we're told a particle is projected up from the base of a smooth plane along the line of greatest slope with a velocity of 42 meters per second. The plane makes an angle of theta degrees with the horizontal, where sine of theta is 2/5. How far up the slope does the particle travel before it comes to rest? Well, to solve this, assume the particle has mass m and comes to rest at a vertical height h. Then we can use the conservation of energy. The initial kinetic energy and potential energy is equal to the final kinetic energy and potential energy. Now the initial kinetic energy is a half mv squared, which is a half m times 42 squared. The initial potential energy is 0, the final kinetic energy is 0, and the final potential energy is mgh, which is m times 9.8 times h. Now if we divide both sides by m, we get 882 is equal to 9.8h. And if we divide both sides by 9.8, it works out that h is equal to 90. Now, if d is the distance travelled up the slope, then h over d is equal to sine of theta. So 90 over d is equal to 2 over 5, and if we multiply both sides by 5d, we get 2d equals 450, so d is 225 metres. So the distance up the slope it travels is 225 metres. In example 5, we're told a ball is dropped from a height h onto a horizontal floor and bounces back up to a height of 4/9 h. Find the coefficient of restitution. Now the coefficient of restitution is the speed just after the bounce divided by the speed just before the bounce. Well, to solve this, let u and v be the speeds just before and just after the bounce. Now using conservation of energy, for the descent, up till the point where it's just about to hit the floor, we have initially there's only potential energy, mgh, and finally there's only kinetic energy, a half mu squared. And for the ascent, just after it's bounced, we have the potential energy is 0 and the kinetic energy is a half mv squared. And when it's reached the top, we've got the kinetic energy is 0 and the potential energy is mg times 4/9 h. So if we divide the second equation by the first equation, a half mv squared over a half mu squared equals mg times 4/9 h over mgh. And lots of that cancels. On the left-hand side, the half and the m cancel, and on the right-hand side, the mg and h all cancel. So we're left with v squared over u squared is equal to 4/9. And if we take the square root of both sides, we get v over u is the root of 4 over 9, which is 2/3. So The coefficient of restitution is 2/3. Let's consider the situation we had at the start. A mass M rests on a smooth table and is attached by a light string passing over a smooth pulley to another mass small m. Once released, the mass small m will descend, pulling the other mass along with it. Now, because the string is inelastic, both particles will have the same acceleration. At any given instant, they'll also have the same velocity and will have covered the same distance. Once released, we can find the acceleration of each mass. To do this, we need to mark in the forces on each mass. Now, on the mass capital M, we of course have gravity acting down, and that's mg. And there's a normal reaction acting upwards. We can call that R. Also, there's a tension in the string. That's horizontal, but there's no friction because the table is smooth. Now the mass will accelerate horizontally, and so we can label that A. So, if we resolve horizontally on this mass, using F equals ma, we have T equals ma. Now on the other mass, small m, we have two forces, the weight, which is mg, and upwards we have T. Now this tension T is the same as the tension at the other end of the string because the string passes over a smooth pulley. Now the mass will accelerate downwards with the same acceleration as the other particle, so we can also label it A. If we resolve vertically downwards, we have mg minus T equals ma. Now, if we substitute T from equation 1 into T in equation 2, that gives us small mg minus capital Ma equals small ma, or mg equals capital M plus small m times A. And we can divide all the way through by m plus m to get A equals mg over capital M plus small m. Now suppose after some time they have both travelled a distance h, and both now have a speed of v. For either one of them, let's say mass capital M, we can use v squared equals u squared plus 2as, and we have the initial velocity is 0, so v squared equals 0 squared plus 2ah. And if we divide by 2, we get a half v squared equals ah. Now, if we substitute a from equation 3 into equation 4, that gives us a half v squared equals small mg over capital M plus small m, all times h. If we multiply across, we get a half into capital M plus small m, all times v squared equals mgh. And if we expand the brackets, that gives us a half capital M v squared plus a half small m v squared equals mgh. Now, a half mv squared is the kinetic energy. So on the left-hand side, we've got the total kinetic energy of both particles. And on the right-hand side, mgh is the potential energy. Now the mass has descended, so that's the potential energy lost. So we see the total kinetic energy gained by both masses is equal to the potential energy lost by the mass small m.